Hello everyone, welcome to the third lecture on elasticity. In the last few classes, we discussed what is meant by the elasticity, what is the different properties of material showing elasticity, what are elastic constants, and how important they are for the different mechanical properties of the material. In the next few classes, we will discuss about how we can determine this elastic constant using different experiments. So in today's class, we will discuss about rigidity modulus. So that is about the shear stress and shear strains. So we will study this one using an example of say cylinder, and we find out what is the external twisting couple. Then later on we will relate that expression for determining rigidity modulus of different material using different methods. So now consider an object like this, and we are twisting the object due to this applied torque. So we are applying a torque at this distance. Due to that, there will be a twisting happen to this particular object, and it is called the torsion. So when we twist this object, the amount of resistance a cross section has against these torsional deformations. So the material, the object will form a resistance against this torsional deformation happen to this object. That is called the torsional rigidity of this object. So we can define the twisting couple or torsional couple, which is the restoring couple developed in an object when it is twisted. So when we are twisting in this direction, there will be a restoring couple form in this object which will be in the opposite direction in order to make it stable. Now let us consider a particular example where a twisting happened to a cylinder. So which is called the torsion of a cylinder. So consider a cylindrical rod like this, which is of length L and radius R, and the coefficient of rigidity of the material of the cylinder is eta. The upper end of the cylinder is fixed, and a couple is applied to the lower end, which is a plane which is perpendicular to the length of the cylinder. The OO dash is the axis of the cylinder, and AB is which is a line which is parallel to this OO dash axis. And after twisting, so when we applied the twisting at the bottom of this cylinder, this point B shifted to B dash. So the line AB become AB dash. So there is an angular strain created which is called the shearing strain, which is defined as phi. So we can define phi is equal to BB dash divided by this length, where we approximated tan phi is equal to phi for small angles. So we can define BB dash is equal to L into phi using this particular triangle. We consider the triangle BAB dash. Now let us consider the cylinder is consisting of a number of small cylinders. So it is consisting of cylinders of different radius. So this is the cross section of the cylinder. We take a cross section of the cylinder and we can obtain. Now let us consider a cylinder of radius x. So this is the radius of the cylinder R. Now we consider a different radii of cylinders. So this cross section make a disc, and the radius of this particular disc is x. Now this theta, which is called the twisting angle. So when we twisted at the bottom of this rod, there is a twisting angle which is defined as theta. So the displacement happened to this object, this cylinder, which will be maximum at the rim, which is BB dash, and it keeps decreasing, and at this center it becomes zero displacement due to this twisting. So using this twisting angle theta, we can also define BB dash. So that is the angle is equal to arc by radius. Using that expression for small angle, again for small angle, theta is equal to BB dash divided by the radius, which is small r. So that we can also define BB dash is equal to r into theta. Now we have got two expressions for BB dash, that is BB dash is equal to L phi using the triangle BA B dash, and using the triangle BOB dash it is also equal to R theta. From this two we can we will get the expression for shearing strain, that is phi is equal to R theta by L, where L is the length of the cylinder. From the definition of the rigidity modulus, which is the ratio of shearing stress and shearing strain. So the shearing stress is equal to rigidity modulus into shearing strain, which is equal to the rigidity modulus we define as eta times R theta divided by L. As we discussed earlier, we can consider the cylinder as consisting of number of coaxial cylindrical shells. A cylinder can be consisting of a number of coaxial shells as we see here, and which is one of these shell is this one, the shaded region, and let x be the radius of that shell, and if ds is the thickness of the shell, then area of the shell will be the 2 pi x, which is the surface area here, into thickness. So 2 pi s ds will be the area of the shells. Now the area of cross section of the shaded cell is 2 pi x into ds. Now the shearing force on the shell, which is equal to shearing stress into area. So we define the shearing stress as the force per area, so that the shearing force on the shell is shearing stress into area. So we consider that small shell and the shearing force happening on that particular shell will be the shearing stress into area of the shell. So that is the eta into x, because the radius of that particular shell is x. Instead of r we need to use x into theta by L into 2 pi x into dx, that is equal to 2 pi eta into theta divided by L into x square dx, which is the shearing force on the shell of thickness dx. Now the moment of this force about the axis of the cylinder can be defined as which is the torque. The moment of force is force into distance, where we applied this torque. So that is the moment of force is equal to this force, the shearing force, into x, that is 2 pi eta theta by L x square dx into x. This is the moment of external couple acting on the cylindrical shells. Now the moment of external couple for the entire cylinder, expression we got is the moment of couple happening on this particular shell of thickness dx and radius x. Now if you want to know what is the total moment of couple happening on the whole cylinder, we need to consider shell with radius from 0 to r. So we can integrate that expression from for x values ranging from 0 to r, so that we will get the total external couple happening on this particular cylinder. So that is what we are doing here. That is the moment of external couple for the entire cylinder, which is tau, is equal to integral 0 to r 2 pi eta theta by L into x cube. Now this become x cube dx. So that is equal to 2 pi eta theta by L. So when you integrate x cube, that is x raised to 4 by 4, which is from 0 to r. The value of x is ranging from 0 to r, so that this become 2 pi eta theta by L into r raised to 4 by 4, that is equal to pi eta r raised to 4 theta by 2L. So we can define this is equal to c into theta, where c is the quantity, pi eta r raised to 4 by 2L, which is called the restoring couple per unit twist. So this is the total external couple happening to the cylinder, and if c, we define c as the restoring couple per unit twist. So if theta is equal to 1, tau is equal to c. That is how we define c. So which is the restoring couple per unit twist, which is also called the torsional rigidity of the object. The value of C will be a constant for a wire of given length and radius. Now we will compare the torsional rigidity of a hollow cylinder with the solid cylinder. In the previous case we consider solid cylinder which is completely filled region of radius r. Now for a hollow cylinder there will be an inner radius r1, that is this distance, and an outer radius r2. So within that region only, between R1 and R2 only, the material will occupy. So in the previous integrations, here we only need to take integral from R1 to R2. So we just change the integral from 0 to R2, R1 to R2, so that we will get the total external couple happening to the hollow cylinder of inner radius R1 and outer radius R2. That is tau is equal to integral R1 to R2 2 pi eta theta by L x cube dx, and this will get x raised to 4 by 4 on integrating x cube, and if you substitute from R1 to R2, so that is the only region between the material occupied in a hollow cylinder, so that will be equal to pi eta R2 raised to 4 minus R1 raised to 4 into theta by 2L. So that we can define as the C hollow into theta, where C hollow is the torsional rigidity of the hollow cylinder. And if you are comparing this C hollow with C solid, the C hollow by C solid will be R2 raised to 4 minus R1 raised to 4 by R raised to 4. We just compare the expression, equation number 1 and equation number 2. Since the hollow and solid cylinders are of same material, we also consider they are of same mass. So the mass of the solid cylinder is pi r square L into rho, where pi r square L is the volume of the solid cylinder, rho is the density of material. The mass of the hollow cylinder is pi into r2 square minus r1 square into L rho, where r2 is the outer radius and r1 is the inner radius of the hollow cylinder. From these expressions, r square is equal to r2 square minus r1 square. Now this r2 raised to 4 minus r1 raised to 4 can be written in this format, that is r2 square plus r1 square into r2 square minus r1 square. That is a square minus b square is a plus b into a minus b format. Now, so that the equation number 3, this expression can be rewritten as C hollow by C solid is equal to R2 square plus R1 square divided by R square. But R2 square plus R1 square should be always greater than R square. So if you are considering any hollow cylinders, this combination R2 square plus R1 square should always greater than R square, so that this C hollow is greater than C solid. That means the twisting couple on a hollow cylinder is always greater than twisting couple on a solid cylinder of having same material, same mass and of same dimensions. Hence, hollow shafts are preferred over solid shaft in rotating machineries. Now you have a problem here. In order to calculate the twisting couple on a solid shaft of length 1.5 meter and diameter 120 millimeter, when it is twisted through an angle of 0.6 degree, the coefficient of rigidity for the material is given, that is 93 into 10 raised to 9 Newton per meter square. So you need to calculate what is the twisting couple. The expression for twisting couple is tau is equal to pi eta r raised to 4 theta by 2L. Here eta is given, r is given, the diameter is given. From that you can calculate radius. Then length is also given, that is 1.5 meter. From this theta value is in degree, so you need to convert that one into radian. So that is 0.6 into pi by 180, that much radian. Then also one thing, you need to keep every quantity in same unit. So this is in meter, so everything has to be converted into meter, so that you will get this value tau is equal to 1.322 into 10 raised to 4 Newton meter. Here you have 3 problems which will be given as an assignment. Okay, thank you.